Hello, my name is Schlockermann, and I'm a researcher at the Leibniz University Hannover in the Institute of Assembly Technology. I will present the conceptual design of a soft robot for applications in magnetic resonance imaging. This project takes place in cooperation with the Hannover Medical School. The motivation behind this project is the percutaneous tumor ablation with the use case of a liver tumor, like we can see here in the right figure. During the ablation, the interventionalist places an applicator needle at the puncture site and sticks it into the body. The tumor cells can then be killed by a local temperature change through a probe. So we have first applicator placement and then the intervention. The goal of the project is to develop a concept for the safe positioning and insertion of an applicator needle with the help of the soft robotics. With this, we created a list of requirements. Important requirements are that the robot must hold an ablation needle safely and keep it stable at the desired position in addition to its own weight. Also, the robot must be MR safe and must not interfere with the MRI. Also, the length should be variably adaptable to the patient and the target and thus be modular in design. This also makes it possible to replace individual components. Like we can see in the figure of the Hannover Medical School, the procedure is non-ergonomic for the interventionalist and not automated. The robot is therefore intended to facilitate the intervention in a limited space. Here you can see a patient lying in an MRI. Additionally, equipment is here the breathing tube and the ultraflex large 18. The robot should at least be able to travel through the cycle space in order to be able to navigate to other regions of the body in addition to the liver. The robot is attached to the MRI bore. So the first concept I present is the MRTCylon Rob. This actuator is 98 millimeters long and consists of 4 cylinders which are connected at the top and the bottom. In the middle is the stiffness channel, which is filled with coffee powder. When a vacuum is applied, this channel stiffens and so does the actuator. The 3 remaining cylinders have semicircular air channel, and if a channel is ventilated, the actuator performs a bend. To protect the actuator from ballooning, threads are wrapped around the air channels and act as a fiber reinforcement. So initially, analyses were performed using finite element analysis without granular jamming, like we can see here. Here it became clear that the actuator yields under gravity with a deflection of 45.57 millimeters. On the one hand, this deflection can be exploited for later use. If, on the other hand, this is disturbing, it can be prevented to help with granular jamming. In a test rig with 6 OptiTrack cameras, we recorded the actuator positions during actuation. Here, the pressure was increased to 90,000 Pascal in 5,000 Pascal steps. The deflection in the YZ plane on the y-axis and on the x-axis, the actual pressure was plotted. The graph shows the mean values from 3 measurement series and the standard deviation from each other. At a pressure of 90,000 Pascal, the MRTCylon Rob reaches a deflection of about 30 millimeters. This corresponds to an angle of around 16.76 degrees. The second concept I will present is an adoption of the well-known STIFF-FLOP robot of Jan Fraas. The diameter was increased from 25 millimeters to 27 millimeters in this project, and the air channels were moved slightly further away. And we didn't use the external shaft. On the left side, we can see the sectional view of the 50 millimeter silicon module. On the right side, we see the top view, which shows 3 semicircular air channels and a central granular channel. Also here, we performed an FEM analysis, and on the left side, we see 1 STIFF-FLOP module with an external sheath, and on the right side, we see 2 STIFF-FLOP modules without an external sheath. Under 1 bar reinforcement, the both modules have a deflection of 39.4 millimeters, and the 1 module have a deflection of 6.8 millimeters. In the test rig, we tested one module without an external sheath, and in steps of 5,000 Pascal until 80,000 Pascal. The curve is linear, and at 80,000 Pascal, a deflection of approximately 30 millimeters was achieved, which corresponds to a deflection angle of 14.79 degrees, like we can see here. On the right side, you can see the STIFF-FLOP module hanging in the test rig in the beginning and after pressurizing. The angle is calculated with the actuator length and the change in YZ axis, like we can see here on the left side. So in summary, the goal was to create a concept of a sub-robot for use in MRI, and the first results show a potential for the proposed usage as actuators for applications in an MRI intervention like the percutaneous tumor ablation. In the first experiments, the used material do not interfere with the MRI and therefore do not affect the imaging process. Also, their sheath bending is sufficient for a multi-segment software robot like we can see here in the rendering below. Further steps will be the optimization of the actuator dimensions by increasing the diameter and the length. In this way, modularity will be simplified and fewer actuators are needed to reach the target range. Also, the stiffness will be evaluated with different experiments, including the medical diagnostic and ablation tests. So, thanks for this opportunity, and here are my references of this presentation, and have a nice day.